Welcome to the deep dive. Today we're doing something truly special. You sent us a fascinating piece of digital history, and we're going to unpack it together.
Indeed. For this deep dive, we have excerpts from what looks like the original source code for Microsoft BASIC that you shared with us. Really amazing stuff.
Just think about that for a moment. This isn't, someone talking about it or even a polished history. This is the actual raw code, the stuff that powered those very first personal computers.
Uh-huh. It's a remarkably direct look at the foundations.
It really is. A direct look at how software was built, way back then, straight from the source you provided.
Precisely. Our mission today, well, it's to pull out the key insights, maybe some surprising things hidden in this historical code you've given us.
And we want to make it accessible, right? Interesting, even if you've never coded. Because this isn't just about ones and zeros. It's about ingenuity, problem solving.
And the origins of something billions of people, including you, use every single day.
Exactly. Okay, let's dive in. Where do we start?
So looking at these pages you sent, one of the first things that jumps out is the date, right there in the header. September 10th, 1975.
Wow.
And some pages even say August 27th, 1975. That really places it, right at the dawn of personal computing.
Absolutely. And there's that other detail in the header, monitor Albuquerque schools. What do you make of that?
That's intriguing, isn't it? It hints at a very specific, maybe early application or user of this code you found.
Yeah, it makes you wonder, were students like the first ones playing with this? What were they doing?
It definitely adds a layer of historical mystery to the material you've shared. Beyond the date, though, it's crucial to understand what this code actually is. It's assembly language.
Assembly language.
Specifically for the Intel 8080 microprocessor.
Okay, so for those of us maybe like me who aren't programmers, what does that mean, assembly language? And why use that back then?
Think of it as being super close to the hardware. Like you're giving the computer chip very direct, very basic instructions, not abstract commands like in modern languages.
Okay, low level.
Exactly. And back in '75, memory and processing power were incredibly limited. Scarce resources. Assembly gave developers really fine-grained control. They could make programs super efficient, fast, small.
Because every byte mattered?
Every single byte was precious. You couldn't afford to waste anything.
Got it. Now, something else that really struck me looking through this code you provided. The comments. There are tons of them.
Yes. That's a really sharp observation from your review. It's not just a wall of cryptic code.
No, it's like explanations next to almost every step.
Even at this very low level, the developers, Bill Gates, Paul Allen, they meticulously documented their work. It tells you a few important things.
Like what?
Well, firstly, even back then, software was complex. It was hard. These comments were probably crucial reminders for themselves. Why did I do this kind of thing?
Right, not just getting it to work, but making it understandable. Maybe for themselves later, or even for others.
Precisely. It hints at collaboration, or at least, anticipating future changes or bug fixes. It sort of dispels that myth of the lone genius coder working totally alone.
Interesting. So even then, clarity, communication within the code was important.
Definitely. Okay, so we've got the context. Early days, assembly language, Intel 8080, surprisingly well-commented code, thanks to your sharp eyes.
Right.
Now let's dig into some key areas you flagged. And one thing that's immediately obvious is a big chunk of code for floating point routines.
Floating point. Okay, what's that about?
Yes, a substantial part deals with floating point arithmetic. That's basically math, adding, subtracting, multiplying, dividing, but for numbers with decimal points.
Ah, okay, not just whole numbers.
Exactly. And you see labels in the comments you highlighted, like FAVD, FSUB, FMUL, FDIV.
Yeah.
These routines were absolutely crucial for a general-purpose basic interpreter.
Why so crucial? Couldn't they just, stick to whole numbers on those early machines? Memory was tight, right?
Well, for BASIC to be genuinely useful, especially for, say, science, math, maybe even business stuff users wanted to do, it had to handle numbers with fractions or decimals.
Like calculating interest rates or measurements.
Exactly. Or scientific calculations. Floating point routines provided that power. Without them, BASIC would have been, well, pretty basic.
Okay. And looking at the comments around these routines, you pointed out, it looks like they were really grappling with some fundamental problems.
Oh, absolutely. You see comments showing they worried about checking for zero. Dividing by zero is a big no-no in math, right?
Right. Calculator error.
Precisely. And there's actually a comment in the FDIV routine you've spotted that shows they put in a specific flag just to signal a divide by zero error. That would then trigger a message for the user.
Smart. Building in safeguards.
Yeah, and they were also focused on handling overflows and underflows. That's when a calculation gives a result that's too big or too small for the computer to even represent.
So preventing crashes or just weird, nonsensical answers for the user.
Exactly. And you also see mentions of normalizing results, dealing with positive and negative signs. All essential stuff for accurate floating point math.
Yeah.
It's fascinating to see these core mathematical challenges being tackled right there in the assembly code you've shared.
Now here's something really interesting you noted. The comments also show both single and double precision floating point routines. That sounds like jargon to me. What's the difference? Why have both?
That's a great question. Think of it like accuracy versus size, like different rulers. Double precision uses more memory bits to store a number.
Okay.
So it allows for much higher precision, more digits after the decimal point, more detail.
Gotcha.
Single precision uses less memory, so it can be faster, uses less of that precious RAM, but you sacrifice some accuracy.
So like a ruler with millimeter marks versus one with maybe tenth of a millimeter marks.
Exactly. That's a perfect analogy. Double precision gives more detail, but the ruler itself is longer, uses more memory. Even way back then, they were making these trade-offs, accuracy versus speed and memory.
That's pretty sophisticated thinking for the time, given the limitations. Okay, another key area I spotted in the material you sent was about string manipulation. That sounds like it's dealing with text.
Yes, that's exactly it. Strings are just sequences of characters, letters, numbers, symbols, basically text.
And BASIC needed to handle that.
Oh, yeah. For printing messages, getting text input from the user, stuff like that. We see routines like string. The comments you've highlighted suggest maybe string initialization or input. There would have been others for combining strings, comparing them, finding parts of them.
And looking at the comments you pointed out in that section, what challenges were they dealing with when handling text?
A lot of it seems to be about managing the length of the string, how many characters are there, and using pointers.
Pointers.
Yeah, think of it like an address. A pointer just tells the computer where the beginning of the string is stored in memory. And memory management for strings was a big deal, too. Because unlike numbers, strings can be different lengths, right? Hello is shorter than Albuquerque. So the system needed ways to allocate memory for strings as needed and then free it up later. These fundamental text operations are the basis for, well, everything we do with text today. Documents, emails, websites.
Amazing, those building blocks being laid down in 1975. Okay, let's talk about how the software actually interacted with the physical world based on the code you've helped us explore. I saw sections on input-output operations. What's that tell us?
That's all about getting information in and getting results out. How the basic interpreter talked to the outside world.
So like...
We see labels like IMPT, probably reading from a keyboard maybe, or a storage device, and print for displaying stuff back to the user, likely on a teletype printer back then.
A teletype, wow. And I even saw Kaysen and Sarut mentioned in the code you shared. Those sound specific.
You're right. Kaysen almost certainly means cassette in, reading data from a cassette tape. That was the storage medium for early micros.
Like saving your program on a tape.
Exactly. And CRO probably stands for carriage return out, controlling the teletype printer, moving to the next line. These labels really root the code in the specific hardware of that era.
So the code wasn't just abstract math. It had to know how to drive these specific machines that maybe those Monitor Albuquerque schools users had.
Absolutely. And the comments also mention I/O error handling, which you've probably noticed.
Yeah.
What if the tape is bad or not there? The code had to anticipate these real-world problems.
Building in robustness, even then.
Trying to, yes.
Yeah.
Even if it just meant printing an error message instead of crashing.
Okay, moving on. Sections in the code you sent on memory management and system initialization. Given how little memory they had, this must have been vital.
Oh, absolutely fundamental. Routines like memsize that would figure out how much memory was actually available in the computer it was running on.
Because it could vary.
Yeah, different machines, different configurations. And init would handle the initial setup when you turn the computer on, setting up data structures, getting the interpreter ready to run basic programs.
Like clearing the decks.
Pretty much. And you might also see, often early on, what's called a symbol table. It's like a dictionary within the code, giving names to important memory locations or values. Makes the code easier for the developers to read and manage.
So memsize finds the memory, ini sets things up, like setting the stage before the play starts.
Exactly. And you might find constants defined there too, like the basic version number, maybe system parameters, setting the rules right at the beginning.
Now, trying to picture how it all worked. There must have been code that took the actual basic commands someone typed like print hello and turn them into machine instructions. That sounds incredibly complex.
You're hitting on syntax and expression evaluation. That's where the interpreter would parse the basic code, analyze its grammar, and then figure out how to execute it, calculate math expressions.
Looking for clues in the code you shared.
Yeah, looking for keywords or comments mentioning formula evaluation or parsing could point to this section.
So it's like a translator. Human-readable BASIC into the machine's own language. Wow.
A very clever piece of engineering, definitely. The comments there, if we dug deep, would probably reveal the algorithms, the data structures they used. It's complex, even for simple basic commands, to break them down and run them correctly.
Finally, one thing that really stands out in the code you provided, and we see this today too, is error handling. Lots of error messages seem baked in.
Yes. Seeing messages like UCL syntax error or UCL overflow is a clear sign that developers knew users would make mistakes. It's inevitable.
And these messages helped users figure out what went wrong.
Hopefully. Rather than just having the program mysteriously stop and crash, it shows a degree of consideration for the user experience, even back then.
It's interesting they had that foresight.
It really is. And the fact that errors often had specific codes, like UCL, along with the message, that suggests a structured way of reporting errors. Easier for developers to debug, maybe easier for knowledgeable users to understand.
Okay, so as we've been digging through this amazing code you shared, what are some of those moments or just really intriguing details that jumped out at you?
Well, one thing that always gets me is just the sheer volume of code. So many lines of assembly language to do what seems simple now,
Yeah.
like basic math or handling text. It really highlights the effort involved.
Yeah, it's a huge contrast to modern languages where one line can do so much. Really makes you appreciate the layers of abstraction we have now.
Absolutely. We're standing on the shoulders of giants.
Yeah.
Another aha is realizing how fundamental these operations are. Basic arithmetic, text handling, memory management. This is the DNA of the digital world being written right here.
It really is. It underpins everything. And were there any, platform-specific things in the code you sent that might surprise someone today?
Well, the heavy reliance on cassette tapes, like we saw with Casson, that's definitely a blast from the past. Modern storage is just worlds away.
True.
And also just the constant focus on meticulous memory management. Every byte counted. Today, we have gigabytes, often terabytes. We barely think about it in the same way. It puts the constraints they worked under into perspective.
It really does. So as we wrap up this deep dive into the Microsoft Basic source code you provided, what are the key takeaways? What should listeners remember?
Firstly, I think this code you shared is an invaluable window into early software development. It shows the fundamental algorithms, the incredible attention to detail needed, and the huge constraints of the hardware back then.
Yeah, it's a powerful reminder, isn't it, that even the super complex tech we use today started with efforts like this. Problem solving, hard work by pioneers like Gates and Allen.
Exactly. And it makes you appreciate all the layers built on top since then. We're so far removed from this direct hardware interaction now. Looking at this code gives you a real sense of that history.
So for our final thought today, I want to leave you, our listener, with this. Think about how much has changed since 1975, but also maybe how much has stayed the same in principle. The basic need to calculate, handle text, manage data, those are still core. And maybe ponder, what will future foundational code look like as tech keeps accelerating?
That's a great point. It's always building on what came before, a continuous evolution.
Thanks for joining us on this deep dive into a truly foundational piece of digital history made possible by the fascinating source material you shared. Until next time.